Good morning, everyone, and welcome to the Tejano Virtual Events Happy Math Hour. These are your weekly interactive math reviews for Math 1332 and Math 2412. Presented this time by Mr. Eduardo Tintos, Robin Carrizales, and Albert Isasi. This session will be recorded so that you may come back to it later. Also, it is recorded so others who may have missed out on today's events will be able to come back and watch it. Thank you so much for joining us, and at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with information we'll be sharing today. Without further ado, here is Mr. Tintos.
Hello, everybody. Let me just share the presentation. Actually, probably I'm going to start just very quickly to introduce the topic. Today, we're going to be talking about graphs. And one of the typical diagrams that I see for applications of graphs is actually this is supposed to represent a network that is used for AIs. And the way that an AI is supposed to create these assignments is that you input a lot of the code is programmed into the computer, and then we have graphs that kind of like model how the computer works. And basically, this is a problem that is supposed to predict how well a student does based on how many hours the student has studied, the sleep time, and the score in the previous test. And you enter some values in there, and then there's some calculations in the middle, and those are the numbers that you see in the arrows, like 2, 1, 0.7, so on, 0.2, 0.1. And then that creates some values, which then gives a result to the computer, and the computer predicts your score on the next exam, which could be a 67. Now, this might not be very accurate because in the previous exam you had an 84, so 67 is a little bit low. So then the computer sends the information back, and it kind of like creates a new calculation. So this type of model is used all the time in computers, where we have graphs that model how the computer is working. So I just wanted to start by giving you an idea of all of this. This chapter of graphing has a lot of applications in computer science, and it pretty much models all kind of like networks, kind of like how neurons work, or how artificial intelligence works. So there's a lot of applications for graphs. For today, the presentation that I had today, let me just go ahead. I noticed that I created this file, and somehow once I started, I cannot close it. So I decided to start by kind of like giving you a motivation. So welcome everybody to Math Happy Hour. And like I mentioned, we're going to be talking about graphs, Euler circuits, and weighted graphs. And to begin with, a graph, the most abstract definition, it's a set of points that we call vertices, and line segments or curves that we call edges. So it doesn't have to be necessarily lines, although we have a lot of lines that connects those dots. And in my picture, you see 3 different examples. Let me see if I can write on it. Hopefully I can. There it is. So the first graph is actually only the vertices, only the points. And then the second graph actually has also some edges that are connecting. And notice that as it is mentioned, it doesn't have to be just lines, that you can also have like curves. So for example, here we have 2 points, 2 edges, and those 2 points are connected. So those 2 points are connected. Edge, maybe I can call it edge 1, so E1, and then this would be edge 2. Kind of like the left path and the right path. This is actually an example of a multiple edge. So multiple edges actually connect the connect similar vertices. They connect the same vertices. So these are multiple edges because they connect the same vertices. The graph on the right is actually a disconnected graph because it has two different pieces. Notice that there's a piece on the top and there's also a piece on the bottom. And so this would have 1, 2, 3, 4, 5, 6 different vertices and then edges. In fact, we also have what we call a loop, which that's what I did when I started at this point and I went back exactly on the same point. So that's a loop. It's an edge that connects to the vertices is basically like one vertex, is the same point. Starts and ends at the same point. And the last one is an example of a graph that we call a we call it a complete graph because if you have 5 points, it shows all of the connections. And it's also an example of a connected graph because it's just one piece. So this is connected, and the other two are disconnected. And another example where we can use graphs is to model information. So for example, it says 5 mobile phone companies have agreements to roam onto each other's networks displayed below. Draw a graph that represents this information where each vertex represents a phone company and an edge connects two vertices if the corresponding companies have a roaming agreement. And so I have all of the information on the table. Notice that I have Mobile Plus, Talk More, Supercell, Airwave, and Lightning. And as you're going on the rows, it tells you if they have a roaming agreement. For example, Mobile Plus and Talk More don't have it's a no, so they don't have a roaming agreement. But Mobile Plus does have a roaming agreement with Supercell. And of course, Mobile Plus cannot have it with itself because it doesn't really need roaming. Usually they use a different network, so you use your own network. So none of the companies have doesn't need a roaming agreement with itself. And so I started by doing 5 vertices because there's 5 companies. And then so each company, remember the names, Mobile Plus, Talkmore, Supercell, Airway, and Lightning. So each dot represents a phone company. And if they have an agreement, I put a connection. So I put the table to kind of like help me out. So I need an edge between Mobile Plus and Supercell. And so I have it there. Mobile Plus is connected to Supercell. And similarly, in fact, on the first row of the table, I have 2 yeses. So that indicates 2 edges, one with Supercell and the other one with Lightning. Then I go to Talk More, and Talk More has only a agreement with Supercell. So we have that edge. And when I went to the row of Supercell, I have a connection between Mobile Plus and Talk More and Airwave, but I had already done 2 of those edges, so I don't need to add an extra one. So the connection, you already see the connection between Mobile Plus and Supercell is already there. And so it is with Talk More, so I don't need to add an extra edge for those ones. Only with Airwave, which is why only one edge, only one line was created. And last, when you get to Airwave, the only other that we need to create is Airway and Lightning because there's an agreement between them. So this is the graph that represents that table. So it's pretty neat. Often in mathematics, we can answer a question simply by looking at a graph. Sometimes looking at the table, it has all of the information together. So having the graph, it is very, very helpful. And I have some questions to demonstrate this. Number 1, it says, which company has roaming agreements with the most carriers? Well, if I look at the graph, all I need to look is for the vertex that has the most connections. And if I look to all of them, like Talkmore, Mobile Plus, Lightning, Airway, and Supercell, the only one that has three connections is Supercell. So the company that has roaming agreements with the most companies is Supercell. And similarly, the company that has only one agreement with one other network would be Talkmore. And we could see there's only like one edge. It almost looks like there's only like one road to get there, to get to Talkmore. At this point, we also need to know what are equivalent graphs. If we want to do more with this graph, we need to be able to distinguish them. And so equivalent is kind of a way of saying that it is the same graph. But we use the word equivalent because they may not look the same. So equivalent graphs have the same number of edges and vertices, and the edges form the same connection of vertices. This would actually be an example of three equivalent graphs. So when you look at them, it actually seems that they're different because we see different letters. But if you start analyzing the graph, you will notice that A is only connected to B, and you could see it in all three graphs. A is only connected to B. B has connections to C, D, and E. You could see it in all three. So B has connections to all three, C, D, and E. And then B has connections. So even these, all of these represent the same graph, even though they look different, because they have the same vertices and exactly the same, I would say the same edges, like the edges are created exactly in the same, with the same vertices. So each one has a vertex between B and D. Each one has a not a vertex, an edge, which a connection between B and D. So even though all of the three graphs look different, these are all equivalent. So for all purposes, I don't need all three. I could just keep one of them that represents all three, even though they all look different. In example 2, this is an exercise. It says determine whether the following two graphs are equivalent. And now I was trying to trick you. The first answer would be yes, because you look, they seem to be exactly the same shape. But when you analyze a little bit better, you'll notice that you have that the vertices are labeled different. And so the vertices are actually the same. They have the same amount of vertices. Each one has 5, which these are the points. But the left graph has different connections. So for example, there's an edge between D and A. Let me highlight it. And there's an edge between D and B. And on the right graph, I noticed that D is actually connected to C, is connected to B, and is connected to E. So even though they have the same shape, they're actually not the same graph. These are not equivalent, because when you look at that vertex, which is D, it has different connections. On the graph on the left, there's only 2 connections. The graph on the right, D has 3 connections. So if I was using this graph to represent networks, it doesn't really make sense to, because the graph on the left has only 2 connections and the other one has 3, so it's not accurate. Okay, so the graphs are not equivalent. They kind of seem and they looked equivalent, but they're not, because they don't have the same connections or the same edges. Notice that this time I use 2 letters to represent an edge. So usually like 1 letter represents a vertex or a point, and you can use, for example, DA to represent the segment, the edge that connects those 2 vertices, DNA. The next definition is that one of paths and circuits. A path is a graph that can be thought as a movement from one vertex to another by transversing edges. So what we expect a path to be, kind of like a road that you're following the edges. You're traversing or you're traveling along the edges. That creates a path. If a path ends and starts at the same vertex, then we call it a closed path or a circuit. I'm just gonna use the word circuit. So it's kind of like it's a closed path. So you start and you end at the same point. And I put some examples. So in this graph to the right, we actually have a path which would be starting on A and then you go B. So let me see if I can write on it. Then you go to B, doesn't matter which one you use. And then you go back to A and then you go to C. So this is a path. It's kind of like a road that you're following to get from A to C, but passing through B. An example of a closed circuit would be A, B, C, and then D, and I could go back to A. Huh? That was kind of a long circuit. Notice that if you just put A, B, A, that would be like a shorter circuit. So just starting at A, going to B, and coming back, that would be kind of like a quick example of a circuit. So you end on A, B, A. But if you want to have a longer one, then that would be A, B, C, then D, and then A again. So there's a lot of those, huh? There's a lot of paths and a lot of circuits, and you could do a lot of things, like you could travel along the same edge multiple times. You could pass the same vertex multiple times. So there's a lot of possibilities of creating paths and circuits. Well, from all of those, there's a special one that is called an Euler circuit. And an Euler circuit is a circuit that uses every edge, but never uses the same edge twice. And notice that we don't need to actually, like the path, this circuit may cross through vertices more than one. So the only important thing for Euler, and by the way, I'm pronouncing it kind of like with oil. I should probably write it down, Euler, because this is a German name. It was a Swiss mathematician, maybe then Swedish, I probably should say. And he lived around the 1700s, and he actually solved a question, and he started a lot of this theory of graphs and Euler circuits. And so on his honor, to create a circuit that is called an Euler circuit is one where you use all of the edges, but you don't repeat. Let me say it like that. You don't repeat. You may pass through vertices multiple times. The only thing that matters is that you don't repeat edges and that you use every edge. And so on this graph, I want to create an example of an Euler circuit. So I need to travel through all of those edges. And so I could start on B and then go to D and then go to F, go to H, passing through G. So it technically should be like F, G, H. And then I can go up to E, right? I can go across all the way till A. I can go to D and then G, and then E and B. So this diagram shows you that this graph actually has an Euler circuit because I was able to travel all of the edges without repeating an edge. So I use different ones. And it's a circuit because I started at B and I ended at B. Notice that I passed through multiple points more than once. For example, when I started, I passed through D, and then as I was finishing, I came back and passed through D again. So that doesn't really matter. That's why we say that the path may cross through vertices more than once. The only thing that matters is that every edge is used so that you travel through every edge, and that you never use the same one twice. So you got to use different ones. And so I wrote the entire, like the sequence of letters that you would use to represent that path would be B, D, F, which is just listing the vertices on the order that I am traveling, that I am transversing the graph, or traversing the graph. Another example is, it says, does the graph shown below have an Euler circuit? So this is an exercise. Can we find one of these Euler circuits? Remember, I have to start and end at the same place, and I need to travel through all of the edges. And I started on B. It doesn't matter. You could start whatever you want to. Usually, it doesn't really matter. So just pick one point and then see if you can find it. And I tried to kind of like find one of these circuits. So I went to B. I put arrows to kind of like indicate. I went to E, and then C, and then G, and D. From there, I need to use now back to F. And notice that when I get to F, I kind of like get into a problem that if I go back to B, if I go to C, better said, then I cannot get out of it because there's only like one path left. And if I go to A, it forces me to go down to E, and then at that point I have nowhere to go and I didn't cover everything. So technically I cannot go to C or A if I want to travel the entire graph. My only possibility is go back to B. But if I go back to B, I didn't really use all of the edges. So this is not an example of an Euler circuit. I wasn't able to do it. And one of the problems that I had is that if I had gone to C, there's no way that I would get out of it because there's only like 3 edges connecting and there's only one left. And something similar happens on B. So I want to think about this in more detail without doing the whole path. So imagine that you start anywhere. Well, at some point you need to get to B and use the 3 edges that are connecting B. And so in this diagram, I put an arrow indicating that I'm going into B by using that specific edge. And then you can use any of the remaining 2. I already picked the one that goes to G. So I'm gonna exit through that edge. Well, right away, I realized that I have an issue because at some point I need to cover that extra path, but I wouldn't be able to create the graph because once I go into it, I would not be able to get out of it since there's no more available edges. So this is an example of a graph where it is impossible to find an Euler circuit. It doesn't matter where you start. You could start on A, on B, on C, on E, F, G. It doesn't matter where you start. That vertex, that point B, creates a problem. And what created the problem is that I had a way to go in and get out, but then there was an extra edge. So similar, the same thing happens with points or vertices C, E, and G, because each one has 3 connections, and I can go into it and get out of it, but then that extra one, I cannot travel it anymore. So this gives me an idea of how to identify graphs where you can actually do these circuits, where you travel through all of the edges. And we call, this is a result that we can state. This result is called the Eulerian graph theorem. And what it says is that you have a connected graph. This is a graph that it is in one piece. It's gonna be Eulerian if and only if every vertex of the graph is of even degree. In other words, to avoid that problem where I have an extra edge that I just cannot cover, I need to have a way out of it. So when you have a way in, you need to have a way out. So that implies that every vertex needs to have an even number of connections or an even number of edges. This number of connections is called the degree. So the number of edges that meet at a vertex is called the degree. So in order for me to have an Euler circuit, which is a circuit or a path that starts at one point, ends at the same point, and it covers all of the edges, I need every vertex of the graph to be of even degree. And I wanted to do one more example about Euler circuits. It says, does the graph below have an Euler circuit? If so, find one. If not, explain why. So if you find one, then you just need to list like where did you start it and what is the order that you follow to find it. But because I just realized about that Euler theorem or result that I mentioned before, that all of the vertices needs to have a way in and a way out, so they need to have an even degree. I started by looking at the degrees of all of the vertices. And so I noticed A has 4 connections, so it's degree 4. B has 4 connections, so it is degree 4 as well. C has 2 connections, so it is a vertex of degree 2. And then I got to D, and funny, it looks like a hand. It has 5 connections. And this is like a bad vertex. So I would never be able to cover those 5 because if I use them in pairs, I could go in and get out, go in and get out. But then the 5th one, which is the last one, I wouldn't be able to cover it anymore. So I need to have even degree or even amount of connections in order to travel all of the edges, starting and ending at the same place. So the answer is no, since there are 2 vertices of odd degree. And so D was not the only one. E also has the same issue because it has 3 connections only. But if you have only one vertex, like as long as you find one vertex that has an odd amount of connections or that it is of odd degree, then that is enough to conclude that it is impossible to find a single Euler circuit. So now that we have this result, we don't really need to get started by finding the graph right away. What I need to do is find the degrees first, and then if it has it, then I go and try to find one. So Euler, this result and this Euler guy, actually, he resolved a problem in the 1700s in a city that was I don't know if it still has the same name, Königsberg. And so this started because the people in this town, they wanted to, in the picture that you see, they wanted to take a stroll. They wanted to kind of like walk around the city, but there was rivers, and so they wanted to walk around the city in a way that they cross each bridge only once. They wanted to use all of them and cross it only once, starting and ending at the same place. So that's exactly what I meant. What the definition of an Euler circuit is on his honor, because he solves this problem. He was the first one to realize that you can only do this if every vertex has even degree. And so that's where it started, that theory of Euler circuits. And to the way that we would explain it nowadays, he might have done it in a different way, is that, and I find this very interesting, because when you look at these pictures, you're looking like, well, where are the vertices and where are the edges of the graph? Well, I represented a dot, and this dot represents the land of mass that is on that specific area. So the top land of mass in green is represented by the top dot. And then the mass of land that is in the middle, in that kind of like circle, is represented by that dot. And so the bridges are gonna be my edges of how do I connect these two masses of land. And so There's a bridge, so that creates one edge. There's another bridge, so I actually have multiple edges here because they connect the same vertices. And then on the others, well, I went ahead and did all of them. Huh? So this graph represents that the path that they wanted to take is represented by that graph. And so I went ahead and did it in the standard way. So I put my 3 dots and then 1 dot on the right. And then I did the connections less exaggerated. And you may recognize that before I actually already used this graph where it has like 3 vertices on the left, 1 vertex on the right, and those connections. And now we can answer the question, huh? So Euler realized that it is impossible to do a stroll around the city using all of the bridges only once because there are vertices of odd degree, and we can see them, actually all of them, not just one. There's not only just one, all of them have odd degree. If you look at the one on the right, the furthermost, that one has degree 3 because it has 3 connections or 3 edges. And then on the top, also degree 3. The bottom one also degree 3. There's 3 connections. And the middle one has 5. So it is impossible to do one of these Euler circuits in this city. And the graph represents that. Okay. Well, maybe we don't want to start and begin at the same vertex, at the same point. So instead, we can talk about something that is called an Euler path, where you're using every edge only once. And how do these changes if you're creating a path that might start and end at a different place? Well, we also have a result that says that for a graph to have an Euler path, you need to have 2 vertices of odd degree. And in fact, this is where you're going to start and you're going to end. So all of the other vertices, they need to be of even degree, but your starting point and your end point, they need to be of odd degree. And an example of this would be, imagine that you plan to mountain bike through a national park. So you're gonna go on your bike in a national park. That sounds exciting, huh? Something that I would wanna do. And you want to ride every trail exactly once. And this is a huge place, huh? There's a lot. If you look at the graph, there's a campground A, B, C, D, E, F, G. So there's a lot of stops if you wanna take all of the trails. You can start and end anywhere. So you may start in one place and finish in another one, since someone will drop you off and pick you up. So basically, typically, if maybe the entrance was closer to this one of those campgrounds, then you probably would be more willing to like start in the same place and end at the same place. But if you can set it up in a way that somebody will pick you up in one location and then they will drop you at a different location, then this is more of an Euler path. It doesn't really matter which ones you pick. You pick it in the end because someone is going to go pick you up and someone's going to drop you off. So all you need to do is start in one place, go through all of the edges, through all of the trails, and only once, so you cannot repeat. Because in a sense, you want to make it as you want to travel everything, so you don't want to repeat. And the most efficient way would be not repeating. So you only go through each edge once. Well, based on the map, is it possible to ride all of the trails without repeating any part of the path? And of course, like before, the first thing that I did is like, okay, before I decide to do a path or try it, I need to look at the degree of the vertices. And notice that degree A, let me just probably check that one, has 3 paths or 3 connections. And so that one is of degree 3. And then I went and checked the connections. By the way, in the picture, it's kind of confusing because the word campground D is in the middle, but this path that connects B and E is like a single line. So it doesn't pass through that point that is C. Well, actually, that's the campground D. Sorry, but it doesn't pass through it. That's why it's kind of like on the right. It's separate. So you can go from B to E if you're following the trail, but you cannot go through B and D directly. So I look at all of the degrees. I'm going to skip that part, but I have, if you look at my numbers, I have degree A, the degree of A is 3, and then B, C, they're both of degree 4. D is degree 2, E is degree 4, F is degree 3, and G is degree 2. And maybe I'll just point out on the last one, this is G, and there's like kind of like two connections, one to F and the other one to B. So it's degree 2. And these actually satisfy the result that I mentioned before, that if you don't need to start and end at the same point, what you need is 2 vertices of odd degree, 2 odd numbers, and then all of the other numbers, they need to be even. And that's exactly what we have. We have A is an odd degree and F is an odd degree. So that means this is actually possible. I can actually travel. I could go on this national park and go through every trail exactly once, cover all of them and only once each one of them. And so now that I check that it is possible, then I'm gonna just, and remember, I'm gonna use the odd ones to start and end. So it doesn't matter which one you pick. I started on A and I went to B and then to C, D and E, and then I went back to B, and then from B I went all the way to F, passing through G. So it was B, G, F. And then I decided to go back to E, back to C and A, and then I go back and end on F. So this is kind of like a cute application. If you study graphs, you can actually determine whether these paths or these circuits are actually possible to do or not, just by remembering these results. Well, the next topic is more related to what I started talking about at the beginning with the graphs that model AI, artificial intelligence, and also like a lot of the computing models and network models they contain weighted graphs. And in this section, I'm going to talk about Hamiltonian path. And these numbers I know are kind of funny. Hamilton was another physicist that made contributions in mathematics and physics. He's known in both fields. And on his name, we have something that we call a Hamiltonian path. And in this case, we're interested in visiting each vertex once without visiting any vertex twice. So now we're changing the focus. Instead of like trying to travel through all of the edges, now I want to travel through all of the vertices only once. So I want to go through all of them and do not repeat vertices. And the edges are not important. So it is okay to use the same edge twice, or maybe you don't use some of them. And that is, well, actually it's not possible to use the same edge, but this time I don't care if I don't use all of them. So I only care about traveling, using all of the vertices, traveling through all of the vertices. So a Hamiltonian path that starts and ends at the same vertex is called a Hamiltonian circuit. Because the word circuit in general just means that you start and end at the same time. If you add Hamiltonian, it just means that you're passing through all of the vertices exactly once. And a Hamiltonian graph is one where you can find one of these circuits that pass through all of the vertices exactly once. And we also have a result due to another famous mathematician, Paul Dirac. And Paul Dirac is actually more modern. He was, I think, He's from the 1900s, somewhere around, I'm just going to say 1900s, mid 1900s, I believe. And he actually received the Nobel Prize of Physics for a lot of the contributions that he did in physics. And his result, he realized that if you have a connected graph that has at least 3 vertices with no multiple edges, remember that the multiple edges are those ones that connect the same vertices. So you can have 1, 2, 3 different edges that connect exactly the same vertices. Let n be the number of vertices. So my variable is going to be n, and it represents the total number of vertices. If every vertex has a degree of at least n over 2, then the n divided by 2, then the graph must be Hamiltonian, which means if you want to find one of these Hamiltonian paths or circuits, you need to check that the degree of each vertex is at least n divided by 2. And like I mentioned, what it means by multiple edges is that these are edges that connect the same vertices. And an example of that would be like these are multiple edges because there's 2 ways of connecting A and B. You can use the edge on the top and the edge below. So if you want to find a Hamiltonian path or circuit that visits all of the vertices exactly once, your graph should not contain, it has no multiple edges. So none of this, otherwise it's impossible to find it. Well, let's take a look at an example. The graph below shows daily overnight delivery routes between 7 office locations. Is it possible to send the document through all of the offices and return to the starting office without visiting any office more than once? So this is a great application because when you read it and understand it, you realize that it's asking for these. You gotta visit all of the vertices. You gotta visit every location only once, huh? Because you don't want to kind of like do the trip twice. Like you don't want to like in the most efficient way. So only traveling each and all of the vertices once. And to see if it's possible, the first thing that I did to use the result, Dirac's result, the first thing that I needed to look at is how many vertices do I have? Well, if you count all of the cities, it's 7. And then remember that you're supposed to divide by 2. So 7 divided by 2, that is 3.5. And now I need to check that all of my vertices are at least of degree 3.5. So in other words, since when you create the degree, when you find the degree of a vertex, you're looking for lines. And this is a whole number. So you need to have either have like 3 connections or 4 connections or 5 connections. So if it says at least 3.5, it's better to round it to 4. So that means every vertex needs to have at least 4. If it has less than 4, then it is impossible to find one of these circuits that travels through all of the vertices. And of course, you might already realize the answer is no, because if you look at some of these cities, such as Los Angeles, LA only has it has 3 connections or 3 edges, which means it is less than 4, so it's impossible to do it. And actually, all of the cities are of degree 3, except San Francisco is the only one that actually has the 4. Remember that when we say at least, it means 4 or more. So it could be maybe 4 or 5 or 6 or 7. Anything that is less than 4, it doesn't help you to find one of these paths that travel through all of the vertices. Okay, so how do we get to these weighted graphs? What are the weighted graphs? We're missing that last part. And In a weighted graph, we also have our vertices and our edges, but each edge has a value. So we give a value, kind of like when I show you that diagram of how AI does its calculations, there was numbers between the edges. And so we call this value, this number, we call it a weight. The value, that number could be anything that you want. So it could be any number. You determine that number based on whatever is relevant to the problem. So an example would be a tourist in San Francisco wants to visit 5 locations by bus and then return to their hotel near Moscone Center. The table shows, oh, I think there's a typo. The table shows the travel times between locations. And if you see an A, this means that there's no route available to travel to that specific location. Find 2 possible routes and compare their total travel times. So for example, if I start on the first row on Moscone Center, notice that if I want to go to the Civic Center, it takes me 18 minutes. And then if I want to go to Union Square, that is 6 minutes. And if I want to go to Embarcadero Plaza, that is 22, and so on. And there's actually not a direct bus that would take me to Fisherman's Wharf or Coy Tower. So again, the first thing that I would do is obviously create a graph. Each vertex would be one of these locations where I want to travel. And this time, those numbers, this is not like when I gave the first example of the mobile phone roaming. We didn't have any numbers. It was just yes or no. But in this time, it's actually relevant, the travel time. So the weight of each edge is the travel time. So for example, this is the graph. I have the 6 locations and then I have the connections. Since in the table it says that going from the Moscone Center to Civic Center is 18 minutes, so that edge has a value of 18, which is the travel time. And so the question is, find 2 possible routes and compare their total travel times. Well, to simplify the route, I decided to just use the initials. So M is going to be for Moscone Center, C for Civic Center. The only one, since I had 2 starting with C, Coy Tower, then that one I'm going to represent CT. I'm going to use 2 letters for that one. So CT means Coy Tower. And so one possible way to travel would be starting Moscone Tower and then Civic Center and then Union and then Fisherman's Wharf, Coy Tower, Embarcadero, and ending on Moscone Tower. Because remember that the tourist has a hotel that is near there, so he wants to start and end exactly in that place. And when I do the sum of their weights to find the total travel time, and so I added all of the numbers and it gave me 114. So that's one possible route. Another possible route would be, notice that the first one started at Moscone and it went to the Civic Center. And then the second one that I listed below it starts at Moscone Center and then it goes to Union Square first. And so it travels through all of the places that the tourist wants to visit, travels through all of the vertices. And when I did the sum of all of the times, the travel time, it gave me 113. So it turns out the faster traveling time is the second one. And the question, obviously a natural question is like, oh, I see. So there's different ways of traveling. I want to use the one that would take me the less time, the less travel time. We're not counting how much you're spending in each location, but the one that you would need to be less on the bus. And right now, the second route seems to be the fastest. It's 1 minute less, huh? Not a lot, but it's 1 minute less. And like I mentioned, one natural question is, what is the best route to take? What is the fastest one in this specific scenario? Well, the answer is actually not easy. One method is to list all of the possible Hamiltonian circuits. These are the ones that pass through all of the locations, the only ones. And then you find the total for each one and you compare them, and you choose the smallest. Right now I only did two, but I would need to do all of the possible routes and then find which one is the smallest to see which one takes less time. Well, unfortunately, the number of different possible circuits can be extremely large, like crazy. Like if you have a graph like this that only has like 5 vertices, actually six, I'm sorry, 6 vertices, there are 20 million different Hamiltonian circuits. So even if you use a computer, it's almost impossible to solve this problem quickly, because the computer would need to find all of these 20 million different paths, Hamiltonian circuits, and then compute the traveling time on each one and compare them so that a computer can find the lowest one and tell you like, hey, this is the best sequence. So this happens a lot in open problems in math, that someone starts with a small problem and then they want to have a computer solve it for us, and then we realize, well, using the current methods that the computer uses to calculate is almost impossible. It takes forever. The computer will have to be running days and days just to come up with an answer. And a lot of the research that has been done in computer science is led by these type of questions, because they're trying to make these methods more efficient, and so they have to develop new ways for the computer to make the calculations faster. Um, we do have algorithms to do this. An algorithm is a sequence of the steps that will tell you how to find the shortest method, and this is very related to computer science, and that's why I started saying that AI is modeled by these type of graphs and by this type of mathematics, because computer science uses algorithms, and at the core of those algorithms, there's mathematics, I swear. Last time I was giving a presentation on graphs and computer science, I told everybody like, hey, in the old days, people didn't want to use computers. Like nowadays, everybody needs to learn a little bit about computer science, because everything's just um, updating so fast that if you don't understand that, you're kind of a little bit lost. So I want to emphasize to all of my students in math, if you're good in math, I promise that you're probably good in computer science, and that is useful because computer science has a lot of math in the background. And one algorithm, this is a very simple algorithm. Like I said, an algorithm is a series of steps that would end by telling you how to find the optimal answer. And so we call this the greedy algorithm to find a Hamiltonian circuit. So you would choose a vertex to start at, then travel along the connected edge that has the smallest weight. So you find the smallest time, and then you use that path. If there's more than one that have exactly the same weight, then it doesn't matter which one you pick, just pick one. Step number 2, after arriving to the next vertex, you pretty much do the same process. You look at the traveling time to each location, and then you choose the one with the lowest or smallest traveling time. And you continue this process, is like repeating itself, like in a loop, until you have visited all of the locations and return to the initial point. And so an example where we use the greedy algorithm in this graph, if I wanted to find a Hamiltonian circuit, I would start at any point. I chose A just randomly. So you could pick anything, B, C, D, or E. And then if you start on A and you compare the vertices, if I go to E, I have a 9. If I go to D, I have a 5, and then 6 and 8. So the smallest traveling time is going to D. So I'm going to choose that path. And I just continue like that. From D, the smallest traveling time would be 4. So I go to C, and then B, and then E, and then back to A. And I actually traveled through all of the vertices. And my total way was 26. So we could say like there was a 26 minutes to go to all of this traveling time, visiting all locations, starting at A and ending at A. And so I believe this is the end. So thank you so much for your attention, and I'm giving back the host the controls.
Thank you so much, Mr. Quintos, for that wonderful presentation. And thank you everyone for attending. Next week, I'd like to remind everyone to go ahead and join us for the Happy Math Hour. And next week, we will be having the counting principle, permutations and combinations, probability and odds, and Math 2412, we will have hyperbolas and parametric equations. For today's student success topic, we have preparing researchers, extensionists, and educators for water sustainability, presented by the pre-H2O program. And for next week's student success topic, we will have the EPCC Mental Health Committee. So join us, please, today at 1 and next week at 1 for the student success topic. And we will see you next week. Have a wonderful weekend.